Indexing and performance optimization. Indexing and performance optimization are critical aspects of database design and management to ensure efficient and speedy database operations. Here are some key concepts related to indexing and performance optimization. 1. Indexing. Indexing is the process of creating data structures that allow for quick and efficient lookup of data based on specific columns in a database table. Indexes are used to improve query performance by providing a faster way to locate data, similar to the index of a book that helps you quickly find a specific topic. Indexes can be created on one or more columns in a table, and they can be of different types, such as B-tree, hash, bitmap, and more, depending on the database management system being used. 2. Performance optimization. Performance optimization involves various techniques and strategies to improve the overall performance of a database system. This includes optimizing query execution plans, minimizing disk I/O, reducing network latency, optimizing database schema design, and tuning database configuration settings, among others. Performance optimization is aimed at reducing query response times, improving system scalability, and enhancing the overall efficiency of database operations. 3. Query optimization. Query optimization is the process of automatically or manually optimizing the execution plan of a database query to minimize the time and resources required to retrieve and process the data. Query optimization involves various techniques, such as query rewriting, query reordering, and index selection, among others, to improve query performance. 4. Denormalization. Denormalization is a technique used in database design where redundant data is intentionally introduced into the database to improve query performance. Denormalization can be done by adding redundant columns or duplicating data in multiple tables to eliminate the need for complex joins or reduce the number of queries required to retrieve data. However, denormalization should be used judiciously, as it can introduce redundancy and complexity in data management. 5. Caching. Caching involves storing frequently accessed data in memory for quick retrieval, instead of fetching it from the disk every time it is requested. Caching can greatly improve the performance of read-heavy database systems by reducing the I/O overhead and minimizing the time required to retrieve data from the database. 6. System configuration tuning. Database systems have various configuration settings that can be tuned to optimize performance. These settings include buffer sizes, memory allocations, parallelism settings, and other system-level parameters that can be adjusted to match the hardware and workload characteristics of the database system. 7. Monitoring and profiling. Regular monitoring and profiling of a database system can help identify performance bottlenecks and areas that require optimization. Monitoring tools can provide insights into system resource utilization, query execution times, and other performance metrics, while profiling tools can help identify slow-performing queries, high CPU or memory utilization, and other performance-related issues. These are some of the key concepts related to indexing and performance optimization in database management. Implementing effective indexing and performance optimization techniques can greatly improve the performance and efficiency of a database system, leading to faster query execution, better system scalability, and improved overall user experience. Data modeling using entity relationship diagrams. Entity relationship (ER) diagrams are graphical representations used in data modeling to depict the structure and relationships of data entities in a database system. ER diagrams are widely used to design relational databases and provide a visual representation of the data model, which includes entities, attributes, and relationships. Here are some key concepts related to data modeling using ER diagrams. 1. Entities. Entities represent real-world objects or concepts that are relevant to the database. Entities are depicted as rectangles in an ER diagram and represent tables in a relational database. Each entity has attributes that describe the characteristics of the entity, which are represented as ovals or ellipses in an ER diagram. 2. Attributes. Attributes are the properties or characteristics of entities, and they describe the data that can be stored in an entity. Attributes are depicted as ovals or ellipses in an ER diagram, and they are associated with the corresponding entity. Attributes can be classified as simple or composite, and they can have different data types, such as string, integer, date, etc. 3. Relationships. Relationships represent the associations between entities in a database. Relationships are depicted as lines connecting entities in an ER diagram and can have different types, such as one-to-one, one-to-many, many-to-many, etc. Relationships are typically named to indicate the nature of the association between entities, and they may have attributes to capture additional information about the relationship. 4. Cardinality and multiplicity. Cardinality and multiplicity represent the number of occurrences or instances of one entity that can be associated with another entity through a relationship. Cardinality refers to the maximum number of occurrences of an entity that can participate in a relationship, such as 1, 0, or many. Multiplicity refers to the minimum and maximum number of occurrences of an entity that must participate in a relationship, such as 1, 0, or at least 1. 5. Keys. Keys are used to uniquely identify entities in a database. Primary keys are unique identifiers that uniquely identify each row or record in a table, while foreign keys are attributes that establish relationships between tables. Keys are depicted as underlined attributes in an ER diagram, and they are used to enforce data integrity and ensure data consistency in a database system. 6. Normalization. Normalization is the process of organizing and structuring data in a relational database to eliminate redundancy and ensure data integrity. ER diagrams can help identify potential redundancy in the data model, and normalization techniques can be applied to normalize the data model to eliminate anomalies and ensure efficient storage and retrieval of data. 7. Notation. ER diagrams use specific notation to represent entities, attributes, relationships, and other components of the data model. There are different notations used in ER diagrams, such as chain notation, crowsfoot notation, and UML notation, among others. Each notation has its own symbols and conventions for representing entities, attributes, and relationships. These are some of the key concepts related to data modeling using entity relationship (ER) diagrams. ER diagrams provide a visual representation of the data model, which helps in designing and understanding the structure and relationships of data entities in a database system. Properly designed ER diagrams are important for creating well-structured and efficient relational databases.
Thanks for watching. For more information, like, comment, and subscribe our channel.